Thank you, Katie. So I will switch gears a little bit and talk about protoplanetary disks, mostly from a perspective of gravity and how they influence the orbits of planets in general. Right. So this is work that I've done with my collaborators, mostly in Toronto. And the main motivation here is that we have these images, very beautiful images, pointing towards these substructures in protoplanetary disk. And we try to infer essentially what is causing these structures. In particular, they might be caused by planets. We know about gaps, rings, and cavities. And we also know of shadows in outer disks that could be casted by inner disks that are inclined. Those might be related to processes of these planet interactions. And something that I'm particularly interested in is trying to understand what happens once the gas disk goes away. Do you have any imprints of these processes that you can try to observe in mature exoplanet systems? And by signatures, I mean eccentricities, stellar obliquities. And when you have multi-planet systems, whether you can have imprints on mutual inclinations and also orbital resonances. So this is the idea, and I will rely mostly on the effect from the gas being dispersed. The main goal is trying to understand whether the dispersal phase has an effect, a dominant effect, on shaping the orbits of all planetary systems, but also the reverse, trying to understand whether we can invert this arrow and try to understand how planets and these are interacting with each other based on some particular systems that we observe. So I'll try to convince you that you can do this too. But let's see how it goes. So I'll start with this sketch. This is trying to give the setup of what are we considering here. This is a rendering from a simulation by Xianghuan Zhu. And the idea here is to show that if you have a massive enough planet, you're going to open up big cavity. We know that. If the gas disk in particular, the inner one is inclining to the outer one, if it is massive enough, the planet can break the disk in two, and they can both be sort of like freely precessing. So you decouple the gas disk. This will be important for the second part of the talk. I will place a giant planet to essentially maximize the effect on an inner planetary system. And the planet will be somewhere in the few AU regime. The idea here is that we know that most of the gas giant planets actually live here based on radial velocity surveys. And also, it roughly coincides with the gravitational radius for photoevaporation. So I will assume that photoevaporation actually happens. You deplete an inner cavity very quickly. You're left with a set of planets, and then let the system evolve and try to see whether something happens. OK. So let's go with the first application. This is one particular system that is fairly interesting. It's called Kepler 419. And I argue that this is the first system that we can say, just based on dynamics, that has been sculpted by the dispersal phase. Right? So these are the specs of the system. You have a cold Jupiter, so a planet at roughly 2 AU, with some eccentricity. And what is striking about this system is the eccentricity of planet B, above 0.8. OK, we know many eccentric planets. That's right. But given that inclinations tend to be small. Something? OK. Thank you. Right, so some processes that are normally invoked to explain high eccentricities, like Lidov-Kozai oscillations, don't really operate here. OK, so that's one piece of evidence that something intriguing may be happening. If now you put the two orbits on the plane, these are well separated. These are essentially like two rings that are interacting gravitationally. And you notice that the solutions give you the eccentricity vector, the orientations of the ellipses being anti-aligned, and they remain anti-aligned over time. So that's really telling you that something is placing the planets in this very particular location. It actually argues against the planet-planet scattering scenario to explain the system. OK, so which process is causing the orbits of this planet? That is dispersal, of course. So I will show a couple of plots where I'm computing here the eccentricity vector of planet B, or the orientation of the ellipse, and the magnitude. This is x and y in polar coordinates. And I'm including initially a very massive disk, and this is actually relevant, in the order of around 10% of the mass of the whole star. When the gas disk is fairly massive, this is the allowed phase space for the planet to move. And something that is important here is that it's only one fixed point, and it happens to be anti-aligned, just a little bit. So you don't have any other choice than just go around this fixed point. You slowly start depleting the gas disk, and if you were close to this fixed point, you have to follow it, sort of like a resonance, up until the point you fully deplete the gas disk, and you're in this very small part of phase space where the error bar of Kepler 490 is B. So this is based only on gravity. And this is based on the idea that you're adiabatically transporting the system towards this new equilibrium. So we argue that this is likely the scenario for this system, and it might have broad implications for general planets like warm Jupiters. In particular, you can produce a set of planets like Kepler 419b. You may even excite eccentricities all the way up to unity that you can trigger high eccentricity migration by tides acting on the planet. But there is a main caveat that we leave here. The model actually uses that there is some initial source of eccentricity in the system. And this is something where I'm actually trying to work on right now, is trying to understand what is giving you this initial source of eccentricity. It could be these torques. Planet C has 7 Jupiter masses, so you might open actually a wide cavity, such that the 3-to-1 linear resonance might be exciting eccentricities. That's one possibility. Or the other possibility is simply planet-planet scattering that in the dispersal phase. So these are things that need to be addressed to gauge the importance of this dispersal at exciting eccentricities. Okay, so this is a nice, concise system for which you can say something about the dynamics. And I want to change to a different topic. I talk about eccentricities. I want to talk now about what happens to spin-orbit misalignment angles. Does this dispersal has something to say about this process? So this plot over here is showing the orbital period and the size of the planet. And the different color here, the filled circles, are the ones that are misaligned. And the ones that are light, they might be misaligned or not, but it's not conclusive. Right? So the idea here is that we know about the hot Jupiters. Many of these planets are indeed misaligned. But we're also learning that there are many Neptunes and even Earth-sized planets that are also misaligned. That's kind of interesting. And there's been many proposals from tilting the disk initially from a binary companion. For many of the systems, we don't see the binary companions. Another possibility is that these planets maybe underwent high eccentricity migration, at which point eccentricities and inclination were excited simultaneously, or some planet-planet scattering process. Okay, so we'll argue that this dispersal can do this, at least for some subset of planets. So this is roughly the setup. This is a work in progress with another postdoc at CETA. And the idea here is the following. So I'm solving for the spin-orbit dynamics when you have here a spinning host star, a set of planets, like Kepler-like planetary systems. You have this Jovian that is initially tilted by some initial inclination, and you have a massive disk that you start depleting in time. So this is one calculation. This is a 5-body problem if you wish. Here is showing time and the spin-orbit angle. What you observe initially is that once you start dispersing the gas disk very slowly initially, you only have small oscillations in the order of initial inclination that we gave. We gave 4 degrees. I have these wiggles here. Those wiggles might be the ones that are causing these shadows in principle, when you have this inner disk casting a shadow in the outer disk. But at some point, you cross a secular resonance. So this is a resonance between the nodal precession of this inner system and the nodal precession of the giant, at which point you strongly couple the orbits and you start driving the eccentricity growth all the way up, in this case, to 60 degrees. So a large spin-orbit angle. Okay, this is interesting. This is something that is being discussed in the context of exciting inclinations of disk, inner disk, to cast shadows in outer disk. The difference with this is that we actually know what the final state of the system is, as opposed to the disk-only case. The final state is just having a set of planets. And you can actually compute the equilibrium, a spin-orbit angle, that I call here analytical equilibrium, and it only depends on the relative angular momentum between the inner planets and the outer planet. So it gives a prediction. And of course, it depends on the initial inclination you assume. So you can do the same for a set of initial inclinations of the Jovian. Even 2 degrees causes a misalignment of 30 degrees. And of course, if you go all the way up to 60 degrees initially, the orbit becomes totally polar, which is kind of exciting. Okay. So we have this analytical expression, and I can start trying to put the planets in this diagram. This is the angular momentum ratio. This is the initial inclination you put in the system. And again, I should emphasize that this is a spin-orbit angle and also the mutual inclination with the Jovian. It's both. Just for reference, the shadow region here indicates when the inclinations are in the order of h/r of 0.1. In case you don't need to actually invoke anything else. Right, so the hot and warm Jupiters would be roughly in this region. For these systems in particular, it actually becomes a little bit hard to explain large spin-orbit angles, just because the inner planets are so heavy. But once you start looking at the Kepler-like planetary systems that are lighter, you have this huge range of inclinations for which the spin-orbit angles could be excited to very large values. And most of the phase space is actually polar, so polar angles, 90. There is a tentative connection between this model and reality, in the sense that metal-rich stars tend to have higher obliquities. It's been shown by Visa and I studies of the Kepler sample. And most of the metal-rich stars hosting short-period planets have indeed these outer giant planets. So there might be some connection, at least in a trend fashion. But you can also start putting some particular planets for which we know the inner and the outer, and see where they lie. The first one is the one that I talked initially, Kepler 419. You have 2 giants. They're nearly coplanar. So roughly falls in this range over here. So it's a small mutual inclination between the planets. Okay, that's consistent. We have a system termed Kepler 56 that is a Neptune with another a small Jovian, in which case the astroseismology determined that the spin-orbit angle is in the order of 45 degrees. It would fall roughly here. Okay, so we're still in the h/r region. And then there is HAT P11. HAT P11 is roughly in a polar orbit. It's a Neptune. And it would be, in principle, accommodated by this model as well, assuming an h/r of 0.1. So that's kind of exciting. What is more exciting is that it's a small sample Rossiter-McLaughlin measurements. But if you look at the sample, around 4 or 5 out of 10 are actually misaligned, and many of them are in polar orbits. They would actually fall here. And this is a clear prediction from this model. Okay, so this is work in progress. There is an interesting connection here between the dispersal phase and obliquities of extrasolar planets. Some of the things that I would like to address, going into more details of these dynamics, is how does the model actually depend on the least evolution, on the size of the evaporated cavity, whether you trigger this secular resonance or not, and also the timescales of the dispersal, how it depends, for instance, on things like stellar types, because there are trends with the data, and how it depends on the gap opened by the planet. And similar to Kepler 419, I have the same question. What is the initial source of inclinations? Can you actually assume that the inclination is in the order of h/r? Maybe there are warp outer disk that could cause actually a similar effect. Or again, you have to rely on planet-planet scattering tilting the orbits. this is still to be determined. So I think I'll stop here and take questions. Thank you.
You care about the fact that your planets lie at the h over r line, because you would say these are reasonable initial inclinations to have, and then you'll say, depending on where it falls there, it should get you the final inclination that you show on those lines? Okay, excellent.
Yes.
Thank you.
Yeah, and the idea of this plot is show 3 examples that go in the right direction. For the same inclination, they actually give the right spin orbit angle or inclination. Yeah.
Thank you.
Yeah.
Said at the beginning, your model requires quite a massive disk, right? 10% of the. So the disk is actually much more massive than the planet. So is this a requirement? Or
That's roughly the requirement, yeah. If you were to put essentially all the disk in just one annuli close to the planet, it would be roughly the same mass. But since it's spread out all the way up to several tenths of a U, it's a factor that is several times higher. The planet is already 7 Jupiter masses. So the requirement is in the order of 5 to 10 masses of the planet. I would say 5. You can decrease it a little, but that's in the order of magnitude. Yeah, that's a good point.
Well, like, why doesn't the? I mean, if it's a massive disk, why doesn't it dampen inclinations to basically zero? I mean,
It could damp the inclinations, yes, and that's something that hasn't been really considered. This is the approximation in which you open a wide enough cavity and the cavity is moving out. So it totally decouples. All the distorts go to zero pretty much.
When you make a gap, fine, but how can it have any? I mean, at some point the planet was in the disk, and
and it's keeping an h over r roughly. So the RMS of inclinations is going to be in the order of
h over r a reasonable initial inclination?
It could be. It's a reference value. I would agree that.
I mean, it looks high to me, but I don't really know much about this topic.
If it is uncomfortably high, then I will rely on planet-planet scattering, being able to.
Sure, why not?
It's a reference. What I'm trying to say, because people actually did try to work this out before, there is a paper by people in Chicago, Matsakos and Conegal. They started with 60, 120. It's a slightly different mechanism. So what we're discussing here is that you don't need very large values of inclination to get this process going. You just need to go to smaller planets. And these smaller planets are out there. And you can measure spin orbit angles for them.
Do you have any instinct about how the timescale of the dispersal is going to play into this in terms of what fundamental timescales of the problem? Does it have to either be larger than or smaller than?
Yeah. Well, not fully, but the sense is in order to engage in this resonance and follow it, it has to be an adiabatic process, right? So if you just fix the set of planets inside, the time scale at which you get oscillations here depend on the distance of the planet. So if you start moving the planet really far, you are outside of this regime of being adiabatic for a fixed dispersal time scale. So if you have these that are dispersing quickly, you need a planet to actually put it closer. Yeah, there is a relation between the two. Yeah.